Good morning, friends. Today we'll be discussing about air standard cycles. So first we will look into what is a cycle, what is a thermodynamic cycle, and what is air standard. Okay, as you know, by the definition, a cycle is a set of processes or a sequence of processes whose initial point and final point are same. That means after finishing a final point, it should reach the initial point like a circle. Say, suppose circle starts from this point 0. It goes through point 1, point 2, point 3, and then it has to return back to 0. This is a cycle. Here the properties will be in a cycle, and the properties at initial point and final point are same. Then we can say it is undergoing a cycle. Here as the name indicates, air standard means the working fluid is air. Okay, so let us suppose there is a cycle. To draw a PV diagram, there is a cycle. Initially there will be a compression process, then heat addition process. This is 1 to 2, then 3 to 4, and finally 4 to 1. There is a cylinder inside a piston. So process 1 to is compression, that is it has to undergo from this to this. There will be a movement. So compression takes place because the volume is reducing by this much. So volume decreases and pressure increases. It goes to heat. Then heat is added. So there may be some heater which will heat this gas. If it heats this gas, to maintain constant pressure, this has to expand from again this point to this point 2 to 3. Then 3 to 4 expansion happens. From here to here volume increases, and 3 to 4 air standard cycle means the medium or the gas which is working medium. If the working medium is a air, then it is called as air standard cycles. Here one of the main assumption of air is that always compression ratio expansion index will be 1.4 and Cp and Cv, which we know already. Cp equal to 1.005, Cv is equal to 0.717. These three values are fixed for every process. But in real case, what happens is after 1 to 2, after compression takes place, heat will be added by injecting petrol or diesel. After combustion, what happens? These petrol and gases will be burned, and carbon dioxide, carbon monoxide, steam, these will be produced and will be mixed with air. This air gets contaminated after generally heat addition. That is why the properties of Cp, Cv and gamma will change. So for theoretical assumption, we are assuming it as an air standard cycles. That means Cp, Cv and gamma will be constant throughout the cycle. Okay, that is why it is named as air standard cycle. There are several air standard cycles which are used in practical cases. We will see one by one. So the main cycle is Carnot cycle. This is a ideal or theoretical cycle. Ideal or theoretical cycle. That means this is the cycle which we want to achieve, but it is not possible. There are that we will discuss while explaining Carnot cycle. This is an ideal cycle or theoretical cycle. This will have maximum efficiency because all the process in this cycle are reversible, or process are reversible process, whereas remaining all cycles will have some irreversible processes that we will discuss while explaining those cycles. Here one thing you have to remember is Carnot cycle is the only reversible cycle, and that is why it will have maximum efficiency. But the drawback is here it is an ideal or theoretical cycle. That means practically it is not possible to implement for an engine. Okay. And next cycle is Otto cycle. Here Otto cycle is generally applied for petrol engines. Petrol engines will run on Otto cycle, and another one more cycle is diesel cycle. Here diesel cycle is used in diesel engines. It is used in diesel engines. And again there is another cycle, Brayton cycle. This is used in gas turbine power plant, and also aero engines which are used in aeroplanes also implement this Brayton cycle. These 4 cycles we'll study in this chapter, and we'll try to see how these cycles are implemented to a engine. So first let us discuss about Carnot cycle. In this chapter we will see how cycles are formed by combining different processes, and also for every thermodynamic cycle there is a pattern of processes. Okay, there is a standard template for processes. One of those template is there will be a compression, there will be a heat addition, there is expansion and heat rejection. These 4 will be involved. These 4 processes will be done for every cycle. Only the thing changes is it can be isothermal compression or adiabatic compression. It can be constant pressure heat addition or constant volume heat addition. It can be constant pressure heat rejection and constant volume heat rejection. That is the only thing changes between the different cycles, but these 4 parts are very common for all these cycles. So Carnot cycle basically contains 4 processes. First process is 1 to 2, state 1 to state 2. First process is isentropic compression. And it follows the law PV power gamma equal to constant. Here gamma we have written because it is a air standard cycle. So next 2 to 3 is heat addition. Here heat addition will be done at constant temperature process. You may think that how heat addition is possible in an isothermal process. During reversibility and irreversibility, we have discussed that if there is a finite heat transfer, that means if heat is added at constant pressure and constant volume, there will be a finite temperature difference. That means heat will be flown from a higher temperature body to lower temperature body. That is not reversible because heat always transfers from a higher temperature body to lower temperature body. If you have to take that heat back to the higher temperature body, you require a work input. That is why we are doing it as isothermal process. If you assume that there is a body at 30 degrees centigrade and there is another body at 30 degrees centigrade. If you assume that heat is being transferred from this body to this body, then because these two are at same temperature, it can be reversed also. If this is possible, this is also possible. That is why Carnot cycle is incorporated with isothermal heat addition. So here PV equal to constant, or it is Boyle's law. 3 to 4 is isentropic expansion. And 4 to 1 is isothermal heat rejection. Okay. So if you represent these diagrams on a TS diagram and PV diagram, for every cycle you have to remember TS diagram as well as PV diagram. These two are very important for our study of air standard cycles. So first process is isentropic compression. So here the process will start at this point. The temperature will be raised because of compression. From this to this, the entropy will be constant. S1 is equal to S2. From this, if you add heat, entropy will increase. But here we are doing it at constant temperature. So here temperature is T2. Next, isentropic expansion. If you expand a gas, the temperature will drop because it is isentropic expansion. S3 is equal to S4. And finally, 2 3. Finally, 4 to 1. Heat is being rejected. So the entropy transfer will also decrease. This is the TS diagram for a Carnot cycle, whereas PV diagram will be like this. So at this point we will compress the gas from 1 to 2. So next we are doing it as heat is being added to the system. One to 2. If heat is added, say suppose there is a piston and cylinder. If heat is added, what happens to this gas? This volume will increase. Here, if volume increases, because temperature is constant, volume increases, pressure should decrease. So pressure will decrease and volume will increase. This is the process which is called as isothermal heat addition. isothermal heat addition. Next is isentropic expansion. So pressure will reduce and volume will increase. And last one is isothermal heat rejection. If you want to reject heat from this, you have to gradually compress this, so that, and while compression, this temperature of the gas will increase, and that will be maintained at constant by rejecting heat continuously. So that is why in some textbook it is written as isothermal compression, because volume is being decreased and pressure is being increased, and this is called as isothermal expansion, because volume is increasing, pressure is decreasing. But the correct term to discuss this is isothermal heat addition and isothermal heat rejection. So this will be 3 to 4, 1 to 2, 2 to 3, 3 to 4, and 4 to 1. There are different volumes at different places. Okay, this is how PV and TS diagram will come into picture. If you see this in a practical sense, generally to maintain isentropic process, during isentropic compression or expansion, there will be no heat transfer. There will be no heat transfer. That means here Q 1 to 2 equal to 0 and Q 3 to 4 is equal to 0. During these processes, heat transfer is 0 because these two are adiabatic or reversible adiabatic or isentropic process. This can be assumed theoretically like this. So, say suppose initially the piston is at this position. So this is the total volume from 4 to 0. This is the total volume of the engine cylinder. Initially the position is at 1. So during 1 to 2 process is isentropic compression. So during this process there will be a insulated head. That means whatever the compression takes place, there will be no heat transfer between this gas and outside atmosphere. So it will happen like this. From 1 to 2 there will be isentropic compression. After reaching to 2 to 3 is isothermal heat rejection. So during this process what he will do is this cap will be replaced with a highly conductive material. That means whatever the heat is given to this, it will transfer to the atmosphere. So what happens is, if you recall 2 to 3, here expansion takes place. That means volume is increasing. So now this is at the position of 2. This piston will start moving in this direction. So what happens? The gas will expand. The temperature tries to decrease, but this is an conductive head. So this atmosphere will not let the temperature of the gas decrease. So continuously there will be heat transfer between the surroundings and this gas, because this has to be maintained isothermal process. Temperature is equal to constant. So after this 3 to 4 is expansion. Again at 3 you have to replace the cylinder head with a insulated one, and 3 to 4 isentropic expansion takes place. Again 4 to 1 heat rejection takes place with an conductive head. So this all theory tries to make Carnot cycle work, but in practice this is not possible because of these highly unlikely isothermal heat addition and isothermal heat rejection. Okay, so coming to why we are studying this, even though it is a theoretical one, is because there is a limit how much of work, maximum work that can be extracted from heat. Our subject is regarding this. We have to convert heat into useful work. Okay, Carnot cycle sets this maximum work limit. So beyond this, say this can be explained like this. Say suppose there is a 100 joules of heat. From this 100 joules at a temperature of say 500 Kelvin, and if Carnot cycle says this can be converted into 30 joules of work. That means whatever the cycle you use, this will be the maximum. If you use Otto cycle, that may be a 20. If you use diesel cycle, that may be a 22. If you use Brayton cycle, that may be 18. Every cycle output will be less than this Carnot work. That is why it is very important to understand the Carnot cycle, because it is an ideal cycle, or it is the cycle which can be used to extract maximum work. Okay, so if you run a heat engine using a Carnot cycle, it is called Carnot engine. Carnot cycle, it is called Carnot heat engine, and this will have the maximum efficiency of a heat engine. So if you calculate the efficiency of a heat engine, which here is Carnot cycle, or we can write like Carnot equal to efficiency is equal to output by input, which is equal to output is work and input is heat supplied. Okay, if you take work into consideration, it will be net work. That means there are some compressions and some expansions. During expansion, work can be extracted, that is 3 to 4 work can be extracted, whereas in process 1 to 2 you have to supply work because it is a compression process. So this will be the network. Network means cyclic integral of W. So for a cyclic process, cyclic integral of W is equal to cyclic integral of Q, whereas heat transfers are only 2. Heat is being supplied during the process 2 to 3. This is the isothermal heat addition process. So here heat will go into the system, whereas and also during process 4 to 1 heat is being rejected. During isentropic process there will be no heat transfer because it is an adiabatic process and there will be zero heat transfer. So if you take W net, it will be equal to here Q supplied will be heat input and heat input, that is heat is supplied to the system. So Q is positive, Q supplied, minus rejected heat is negative, Q rejected. So W net is equal to Qs minus Qr by heat supplied Qs. This is written as 1 minus Qr by Qs. Okay. So if you take Qr and Qs, these two are the isothermal heat rejection, isothermal heat addition. During the process, during this process, Q is being rejected during process 4 to 1, whereas heat is being supplied during process Q 2 to 3. So this is an isothermal process. During an isothermal process, heat transfer is equal to MRT. So here 1 to 4, at both the points temperature is T1. MRT1 ln V4 by V1. Initial point is 4, final point is 1. So heat is being rejected, that means minus will be consumed, because we are initially saying heat is being rejected, that is why initial minus by final volume. Whereas for heat supplied, it is MR T2, 2 to 3, here 2 to 3, for 2 to 3 the temperature is T2. So MR T2 ln final by initial, V3 by V2. Okay. These are this has to be supplied substituted in this formula, efficiency of a Carnot cycle, that is equal to here 1 minus Q rejected is MRT1 ln V4 by V1 by MRT2 ln V3 by V2. So if you cancel out MR, the remaining is ln of T1 into ln of V4 by V1, T2 into ln of V3 by 2. We will now get into this. So here to get these relations, process 1 to 2 is adiabatic compression. That means it follows P1 V1 power gamma is equal to P2 V2 power gamma, and also for every process this is constant, P1 V1 by T2, P1 V1 by T1 equal to P2 V2 by T2. So we want to relate between temperature and volume. Okay. So from this you can say P1 by P2 is equal to P2 by V1 whole power gamma. So right, if you substitute this here, P1 by P2 into T2 by T1 equal to V2 by V1. P2 is coming this side, and V2 is coming this side, and T2 goes here. So P1 by P2 into T2 by T1 equal to V2 by V1. If you substitute this here, becomes V2 by V1 whole power gamma multiplied by T2 by T1. So finally T2 by T1 becomes, so this is 1, this is gamma, if it goes that side it becomes V2 by V1 whole power 1 minus gamma. Similarly for 3 to 4, 3 and 4, which is here 3 to 4 process is expansion. If you see here 3 to 4 process is expansion. This is also an adiabatic process. If you write similarly 3 for 3 to 3 and 4, 3 to 4. you write, it will become T4 by T3 equal to V4 by V3 whole power 1 minus gamma. That means here T4 is equal to isothermal process because T4 is equal to T1 and also T3 is equal to T2. This becomes T1 by T2 is equal to V4 by V3 whole power 1 minus gamma. If you reverse this, it becomes T2 by T1 is equal to V3 by V4 whole power 1 minus gamma. This substitute this here. If we equate this, it becomes V3 by V4 whole power 1 minus gamma. These two can be cancelled out, and you can rewrite this as V4 goes here, V4 goes here, and V1 goes here. Sorry, not V1. So V4 by V1 is equal to V3 by V2. So this is similar to this, so you can cancel this also. So finally, efficiency of Carnot cycle becomes 1 minus T1 by T2. Here, you have to observe one more thing. T1 is the temperature of lowest temperature possible in the cycle, and T2 is the highest temperature possible in the cycle. So Carnot cycle efficiency can be written as 1 minus T low by T high. Okay, this is the expression for Carnot efficiency. If you relate this to a heat engine, which says, according to the second law, heat engine is a device operating on a cyclic process cycle. This is the cycle and this is the heat engine, which takes heat here Qs from a higher temperature source and rejects heat to a lower temperature source, which is at a temperature of TL. This is called sink. You can extract heat from this. So here efficiency of heat engine is equal to 1 minus TL by TH if it is operating on a Carnot cycle. Only Carnot engine is reversible engine. In a problem, if he says a reversible engine is operating between, means that reversible engine is a Carnot engine. In the next class, we will discuss about Otto cycle.